There are more weird things in general relativity than what we've seen so far. Let us start with the definition of what is a time-orientable space-time. See, not only can space-time have horizons and singularities, general relativity, in principle, is fine with having a space-time in which it's not even unique which direction is the future, which direction is the past. We say that a space-time is time-orientable, so that it is unique, if at each point of the manifold we can separate the non-space-like vectors, so the light-like and the time-like vectors, into two groups. Namely, one which we will call future-directed, and the other one which we will call past-directed. And that separation is supposed to be such that it is continuous in the manifold, that there's no jump. In that case, we will say that the space-time is time-orientable. Here's a simple cartoon of what could go wrong. Imagine the manifold is simply the surface of a can of soda. And here I drew the light cones. And as you go around the can, the light cones just turn around, become upside down as you arrive back here, right? So if this is the future and that is the past half of the light cone, future here, past there, then you see it tilts, and when it comes back, then you have in principle that all the light cones go continuously into each other, but the assignment of what is future, what is past, has a break here. Because here, suddenly, it flips from, here's the future is up, but then eventually it comes back, the future is down. So even though the light cone structure in principle is continuous, the assignment of what is future, what is past, is not. Now that thing would be bad. We don't think the universe operates this way. But general relativity doesn't care. It allows it. Here's a lemma. When a space-time is time-orientable, so there is a continuous assignment of what is the future direction, what is the past direction, then and only then, that's why there's a double F, then and only then there exists a smooth, non-vanishing, time-like vector field, or then there exist several, well, in the mathematician sense, when there exists a so-and-so, it means at least one. So there exists a smooth, non-vanishing time-like vector field V on M, on the manifold. And you see, what we are making use of here is the fact that if a time-like vector field were to change the direction from pointing future to pointing past, it would have to go through a space-like phase, through a space-like point. So by having it or goes zero in the middle, so by requiring that it is non-vanishing, we are enforcing that the direction in which it is pointing cannot change. Not in a continuous fashion anyway. So if, notice that if such a non-vanishing time-like vector field is given, then we can define relative to it at each point what we mean by future-directed vectors and what we mean by those that are past-directed. Future-directed vectors are then those non-space-like vectors, so time-like or light-like, for which the inner product with our reference time-like vector field V is positive. So it's basically pointing in the same general direction. Whereas if the inner product comes out to be negative, then we say it is past pointing. And, well, this is just the argument that you can't flip sign in a continuous way when you have the the field V non-vanishing. So in what follows, we will always assume that space-time is time-orientable. And we will assume that the time orientation has been chosen. As we just saw, this is equivalent to the assumption that there exists at least one smooth, non-vanishing, time-like vector field. As we will later see at the very end of this lecture today, if we add one more condition, namely if we require this vector field to not only be smooth and non-vanishing and time-like, but if we also require it to be a gradient field, then the space-time has a further very nice property to do with causality, which is basically saying that you can't travel back into the past, that there are no time-like loops, as we will see at the end of this hour. So for now, we are only requiring that there is a non-vanishing, smooth, time-like vector field, and this is ensuring so far only that there is a unique time orientation. Now, with this assumption that I study the structure of cause and effect in a general space-time, in a way that's more general than could be expressed with Penrose diagrams, we will need the terminology that I'll introduce now later on, when I will sketch, not today, but later on, when I will sketch how singularity theorems are proven. So how we can prove that even in the absence of any symmetries, even if we cannot explicitly solve the Einstein equations, we can still prove that the singularity might be unavoidable, or will be unavoidable, in the case of a black hole or a cosmology. Okay, so we begin with a definition that a curve or path from an interval in R into the manifold is called future-directed. It's a future-directed time-like curve if each tangent vector to the curve is the future-directed time-like vector. Okay, so time-like curves are curves whose tangent vectors are time-like. And notice that I'm not making any restriction here to geodesics. It's just any curve. And we assume it to be smooth so that we can always calculate the tangent vectors. But it doesn't have to be a geodesic. Notice that if we consider a pathological path, like the path which just stays at one point for a while, so the parameter of the curve goes on, but you're not moving on the manifold. In other words, when the tangent vector is vanishing, and you're traveling with velocity 0 through the manifold, so to speak, when the 4 vector of velocity is vanishing, then that is not a time-like path, because it's light-like. The length is 0, right? It's not time-like. Time-like means that the length squared of the tangent vector has to be negative. It's not allowed to be 0. It has to be negative. Okay, so gamma dot has to be smaller 0. Now, what if we allow that the path is traveled also in part or entirely at the speed of light? Well, a curve is called a future-directed causal curve if the tangent vector is just not space-like. So now it's allowed to be both light-like and time-like. Again, no restriction to geodesics. This is just a terminology for general smooth curves. Just as a memory aid, time-like curves, obvious tangent vectors have to be time-like. Causal curves are just curves that can cause consistent with causality. So you're traveling at most at the speed of light. So it's consistent with causality. That's why it is called causal. It's a curve that could be traveled by light or matter. In this case, just as a minor technical point that for the singularity theorems comes up, in this case, gamma dot equal to 0, a path that's just not moving in the manifold, is a causal curve. Because the length squared of that vector is, of course, 0, and that technically counts as light-like, and therefore non-space-like. Path-directed time-like or causal curves are defined just the same way. So path-directed causal curves are curves where the tangent vector is pointing towards the past and is not space-like. Now we can define the past and the future of an event. Here's the term to remember. The chronological future, let me close the door. The chronological future of an event P in the manifold is a set called I plus. So I plus of P is the chronological future, and it is consisting of all those events that could be reached from the event P on a future-directed time-like curve. So these are all those events that could be influenced by matter traveling from P onwards. But if it takes light to reach to an event, then that event is not in here, right? So that's the set of all those events that can be reached by time-like paths from P. You can also think of it as saying that an acrochronometer, just as a memory aid, an acrochronometer, a clock with mass, could travel from P to all those points in I plus. By the way, I plus is always an open subset of the manifold, and that's because if gamma is a time-like future-directed curve from P, then any sufficiently small perturbation of that path is also a time-like future-directed curve starting from P. Basically, no matter how fast you travel, slower than the speed of light, you can always travel a little faster or travel a little slower. So that makes I plus an open set. Since, again, a little technical thing, since among the time-like curves, gamma dot equals 0 is not allowed, we have that a point of the manifold is never contained in its chronological future, because it would take a vector of length 0 to go from P to P, but vectors whose a path of length of tangent vector 0 to go from P to P, and that's not allowed because that would be light-like. There's only one exception to this, and that is P can be in the chronological future of itself if the space-time is such that it allows closed time-like loops. And again, general relativity allows that. General relativity allows that space-time has closed time-like loops. We don't think it happens, but there's nothing in general relativity that would prevent that. Now, we've defined the chronological future of an event. That's I plus, all the events that could be reached by chronometers, by stuff with mass. Now let's define the causal future of an event. That's called J plus. And the causal future of an event is the set of all those points, of all those events that can be reached from P on any causal path, on any path that could be traveled by light or matter. So the tangent vectors are allowed to be time-like or light-like. And of course, the plus indicates it's the future. And similarly, you can define the causal past and the chronological past. So with this definition, every event is also an element of its own causal future, because you can write down a path from the event to the event by just staying put, and its tangent vector is going to be the 0 vector, which has length 0, which is okay because it's light-like. And so it is part of a causal path, and therefore every event is in its own causal future, even though it's not in its own chronological future, unless if there are closed time-like curves. Then, as I mentioned already, the chronological past and the causal past, I minus and j minus, are defined analogously as the points reachable by time-like curves, by chronological paths to the past, and by causal paths to the past. Now, we defined the chronological and the causal futures and pasts of individual events. Similarly, one can define the pasts and futures of a set of events. So let's say set S is a set of events. Then we can define the chronological future of this set of events as the set of all those, as the union of all those chronological futures of the individual points. It's a set of all those points that can be affected by traveling chronometers starting from any one of the points S. And similarly, the causal future is the set of all those events that could possibly be affected causally by anything that happens on the event S. And the same with the chronological past and the causal past. Now we are close to event horizons here. Let us define the boundaries of the chronological past and the chronological future and the causal past and the causal future. We denote them with a dot. So here we have the chronological future, I plus, for example, and I plus dot is the boundary of the chronological future of the set of events S. A relevant example is this. Assume S, the set of events that we may consider. Let's say S is the set of events which is traveled by an immortal observer, somebody who travels forever. Now, such an observer has this world line S, the set of all events that it passed through. And that set of events that this observer ever passed through has a causal past. It's the set of all events that could have affected what happens on S. Could have affected them by either stuff that travels with mass or without mass. That's the causal past. So the causal past of that path is J minus, and its boundary, the boundary of the stuff that could have possibly affected our traveler, that's the event horizon of that traveler, if there is such a boundary. If, for example, this traveler is simply staying put in Minkowski space, then this traveler over time will learn about everything that happens or happened or will happen anywhere in the universe. Such an observer will not have an event horizon. But as we saw in the second to previous lecture, observers which are in a space-time with that are in an inflating space-time, for example, will have an event horizon. Now, so far we didn't talk about geodesics. The definitions just referred to smooth paths. Now, for Minkowski space, it's clear that the chronological future of any event is also the set of events which is reachable by future-directed time-like geodesics from P. You don't have to have an engine. You don't have to have a steering ability. You can always just aim things with geodesics. And the boundary is the set of events reachable by future-directed null geodesics from the event P. This is the light cone. But this is not quite true in general spacetimes. And the intuition is, and that is the key insight that led to all the singularity theorems, the intuition is that there can be holes in the manifold, singularities, which are in the way of geodesics. So it may be that you can reach an event on a path that can be traveled by matter by going around a singularity, so to speak. So it's an event that is in an I plus P, but there may not be a geodesic that gets you there because the geodesic would have to crash into a singularity. So this subtle distinction can be used to identify singularities later on. But locally, the situation is always as in Minkowski space. There's this theorem. I mean, apart from those obstructions through singularities, locally it's always like that, also on a curved space-time. Assume that an event, that P is an event in the manifold, and that U is some convex normal neighborhood of the event P. And I made sure what the definition is again. The definition is indeed that any 2 points in U are connected by a unique geodesic. That's what makes the neighborhood a convex normal neighborhood. Okay, so if U is a convex normal neighborhood of P, then these 3 things are true. One is that the chronological future of the event is the set of events that are reachable by future-directed time-like geodesics from P. So we can define this also through geodesics. We can restrict attention to geodesics. We don't have to talk about all smooth paths. Geodesics alone will generate a I plus. And also the boundary of I plus, the boundary of the light cone, or what is often called the light cone itself, the set of events reachable by future-directed is also the set of events reachable by future-directed null geodesics from P. Again, so I plus dot is generated by null geodesics. And one can prove that if an event is in the causal future of P, but it is not in the chronological future of P. In other words, it can be reached if you allow speed of light, but it cannot be reached if you don't allow the speed of light. Well, then, any causal curve between P and Q is a null geodesic. Again, it would seem obvious, but it's not globally because singularities may be in the way. So remember the definitions, the chronological, nothing new here, just a reminder. Chronological future of an event is the set of events that can be reached from S by curves that could be traveled by a chronometer, by stuff with mass, by clocks which have mass. The causal future of a set of events S is the set of events that can be reached in any causal way, traveling at or below the speed of light. And in Minkowski space, we have that the causal future, the causal future of a set of events is the chronological future united with the boundary of the causal future, of the chronological future, which is the inside of the light cone and the light cone. Now, let us study that thing a little more closely here, the boundary of the chronological future. For that, we first need a definition. We say that a subset of events in the manifold is called achronal if 2 points in that subset cannot be reached, cannot be connected by a chronometer traveling, by something with mass traveling. In other words, if there is no future-directed time-like curve between any 2 events of Q. Okay, so Q is called achronal if there is no time-like curve between any two of those points. There may be a light-like curve, but no time-like curve. So Q is achronal if the intersection of the chronological future of that set of events with the set of events itself is vanishing. See, this is the set of all points that can be reached with time-like curves. This is the set Q itself. None of those should be reachable by time-like curves. So if that's the empty set, then it's achronal. Now one can prove that for all subsets of the manifold, the boundary of the chronological future of a set of events is an achronal three-dimensional submanifold of the manifold. I'm talking here, of course, about 3 + 1-dimensional spacetimes. Okay, so the claim is this, that for any set of events in the space-time, the boundary of the chronological future is an achronal three-dimensional submanifold. Which is to say, it's like a piece of a light cone. So here's the set of events in your space-time. Here is everything that can be affected by that. It's the chronological future of these events. It's everything that can be affected by chronometers traveling, by stuff with mass traveling, 45 degrees here if we choose our coordinate system appropriately. However, that line here and that line there is not actually part of I+, because that would require you to travel at the speed of light, when we're just talking about the chronological future. The boundary, though, is that stuff. And that stuff is, these sets of events are always achronal. Cannot be traveled below the speed of light. That's what it says. So the boundary of the chronological future can never be traveled at the speed of light. Can never be traveled below the speed of light. That's what the theorem says. In Minkowski space, if S is just a single event, then, as I mentioned earlier, then the boundary of its chronological future is simply the boundary of the light cone. And clearly, in this case, no 2 points of the boundary, no 2 points of the light cone, of the boundary of the light cone, are connected by time-like paths because they are connected by light-like paths. And here's the thing, though. In general spacetimes, it is clear that when you take the chronological future and you close that set, so you include its boundary, and you get the same as if you take the causal future and consider its boundary and add its boundary. Those are always the same. But in general, because of the possibility that there might be, because of the possibility of singularities, of holes in the manifold, we can have that the closure of the chronological future is not identical to the causal future. And here's the picture for that. Here's an event. This is the forward light cone here. So this is the chronological future. The inside of this is everything that can be traveled at below the speed of light. And let's say here's a singularity. Here is a hole in the manifold. And let's say we just remove it by hand at this point. Don't even need to talk about curvature. We just remove it by hand. Then what do we have? We have that the inside of this cone is I plus P. And what is the closure of I plus of P? The closure is when you take all those points and you add the boundary, right? So now all those points are belonging to I plus bar. And so, for example, this point belongs to I plus bar. All those points belong to I plus bar. But this point does not belong to j plus s. You see that? It does not belong to j plus s, because in order to belong to j plus s, or to j plus of p, there would have to exist a time or light-like path from p to that point q. But they cannot be, because there's a hole in between. You would have to travel straight at the speed of light to go from p to q, because it's just designed in this way. And you can't do any delay. I mean, you can't just circumvent the singularity here, because yes, you could go inside like this, but then you can't catch up with it, because you would have to go shallower than 45 degrees, faster than the speed of light. So there's no way that you can causally connect this event to this event. Therefore, this event is not in the causal future of that event. It is sort of in the shadow of that singularity here. So that means that this point is in the closure of the chronological future, but it is not in the causal future. Yep?
Would you remind me of the definition of the boundary?
Well, you have, okay, so you close the space. Do you know what I mean by mathematically by closing it?
You have to have a topology.
Yes, that's right. And so you look at all the sequences, and then they have to convert.
Topology? Is that like?
Or it's just usual topology.
Usual topology on the manifold.
Yes, on the differential manifold. Yeah, exactly. Okay, so then this leads to the general idea that we will later then see come up in the singularity theorems, that we can use the extendability or non-extendability of curves, especially of geodesics, as an indicator for the absence or existence of a singularity. See, if you write down a geodesic that travels from here to here, then that geodesic runs into trouble. At some point, you can't extend it any further. At this point, you can't extend it any further. So that's one method of identifying the existence of a singularity. But then we have to be careful. It's not easy to capture mathematically what it means that a geodesic cannot be extended. Here is the main pitfall. Let me explain. We say that a point P is a future or past, let's just focus on the future. We say that a point P in the manifold is a future endpoint of a curve gamma. And the curve doesn't have to be a geodesic here. So we say that a point is a future endpoint of a curve gamma. And that doesn't mean that it runs into a singularity, as I will show in a moment. But it is a future endpoint of the curve gamma if for all neighborhoods of the point P, there exists a time t in the time parameter of our curve gamma. It doesn't have to be the eigentime of the path. It's just some parameter time for the path, right? So we're traveling a path, and as we travel it, some parameter that we call t is labeling our path. Okay, so we say that the point P is future endpoint of a curve gamma if for all neighborhoods of the point P, there exists a parameter time t naught from which onwards our path remains in that neighborhood, never to escape again. Okay, so let's say we have here a path that travels through the manifold, and this is our point P, and our path can go on, our path parameter t might go on forever, but if we take here some neighborhood, arbitrarily small neighborhood, there is a certain t naught of the parameter value from which onwards the path will stay within that neighborhood for all subsequent t. Now, it might look like this means the geodesic, or the curve is not extendable, because it never makes it beyond that point P, but it doesn't mean that at all. We could simply be foolish and write down a path which has a finite distance, but its parameter is chosen in such a way that the parameter runs all the way to infinity, and still the path has only traveled like 5 meters, right? And that would make the endpoint an official and future endpoint of the curve. And the endpoint doesn't even have to be part of the path. It could be asymptotically only approached. There's no finite t of the path parameter that would actually get us to the point. So it's a non-trivial issue to see whether or not a path comes to a halt because there's a singularity, or comes to a halt because we have foolishly parameterized. Now, in the above definition, since P is a point in the manifold, any such endpoint is a point in the manifold, right? It is always possible to extend the curve gamma continuously beyond P. Right? So if you have that situation that this point is an endpoint, then, and this point is really a point in the manifold, and the manifold goes on here, then you can always extend by just reparameterizing your path and then continuing the path over here. You can always extend your path so that it actually goes all the way to P and beyond. So what we say is that the existence of an endpoint here indicates not a singularity or a hole in the manifold, but it merely indicates that we chose to end the curve before it was necessary. So we say that a curve gamma is, and that's now the crucial distinction, we say that a curve gamma is future inextendable if it does not possess a future, and the same with the path, a future endpoint. So imagine you have the situation that you have a path parameterized gamma of t, and the path travels happily through the manifold, and you assume you can prove that it doesn't have an endpoint. Assume you can prove that this path does not have an endpoint. Assume you can prove that this path does not obey this. The path does not stay within a smaller and smaller region as you go further and further in time. There is no endpoint in the manifold, at least. There is no P in the manifold that you can point to and say, this P in the manifold is the point towards this is converging. So if there is no endpoint in the manifold, then there are 3 possibilities. So if a curve gamma is not extendable into the future, then either the curve simply runs off to infinity, so could be Minkowski space and you're just staying put. Then you have a world line that runs off to infinity. There is no point in the manifold which would qualify as endpoint, right? Because you're running all the way to future infinity, which is not a point in the manifold, not a point in the space-time. Another possibility for why the curve doesn't possess an endpoint is that the curve runs around forever. It could be that your curve is a closed time-like loop. It would be great. I mean, all of us have made some mistakes in the past, and we could travel on this closed time-like loop and come back to the past. General relativity does not forbid this. So in principle, that is a possibility. That could be one of the reasons why a curve is inextendable. It doesn't have, or another way of putting it is that it doesn't have a future endpoint. And the third possibility, that's the really interesting one, it could be that the path hits a hole. It could be that it hits a singularity. And that this is the reason why it can't be continuously extended. So there's a hole in the manifold, and if there weren't a hole, then you could pinpoint, this is the point P, which would be a future endpoint, but there is a hole, therefore you can't claim that there's a point P in the manifold that does it. These are the places we want to identify. Now, keep in mind that singularities in general relativity are generally not just one point in the manifold. Typically, they are space-like, extended, infinitely many events, or they are time-like. Space-like, for example, would be the singularity of a Schwarzschild black hole. It could be time-like if the black hole is rotating, but nobody is sure about this in a generic case without symmetries.
What's the definition of singularity in the mathematical sense?
Yeah, we are building up to this. Basically, this is our first definition of it. So our first definition as the third case of that classification. If a path it doesn't have an endpoint, and it's not because the path runs to infinity or it's a closed time-like curve, then the only other possibility is this possibility, which we will call the presence of a singularity.
So it's some region that does not belong to the manifold.
Yes, actually, a singularity, you cannot pinpoint and say that it's these points of the manifold. That's right. It's a hole in the manifold. So we identify it through something that is in the manifold, namely inextendable paths. But the singularities themselves are not points of the manifold. Yeah, that's right. And we will, you can classify singularities by the kind of geodesic that identifies them. Because you don't have to consider just time-like geodesics. You could also consider light-like geodesics. You could also consider space-like geodesics. And depending on whether it is space-like, time-like, or null geodesics that identify the singularity by being inextendable, we can then attach a name to the singularity as being either time-like, light-like, or space-like. Now assume, for a theorem, assume that C is a subset of the space-time, which is closed, and assume that an event Q is in the boundary of the chronological future of that set of events. And Q is not in the set of events itself. Then, and I'll draw a picture in a moment, then Q lies on a null geodesic, gamma, inside of the boundary of the chronological future, and the curve gamma, this null geodesic, has a past endpoint on C and is past inextendable because it meets a hole there. Sorry, or it's either this or that. So here it's basically the picture that we had earlier already. So we have here a set of events, and we are now looking at the chronological future of these events. So all the events that can be reached by actual chronometers, by stuff with matter. Here's the boundary, I plus dot. Here's the boundary, I plus dot. And the boundary of I plus dot includes this, includes also that event Q. Because to qualify to be in the boundary of I plus, it just has to be in the completion of that space here, right? So there's no claim of a geodesic existing from the set C to over here. So there are two possibilities now, namely, if, for example, a point Q is over here or over there, then it has a past endpoint on C. See, it can go over here. We can write down a geodesic which ends over there. We can do that. On the other hand, what can also happen is that we are looking at a point over here, and these points are past inextendable. You see, you can write down geodesics here which end over there and which cannot be extended, because there is no way that you can write down a curve past that, because there is a point missing in the manifold. I have to remind you here of the original definition here of what an endpoint is, we say that a point P of the manifold is an endpoint of a curve if, for all neighborhoods of P, there exists a T, so that from all T from T naught, for all T from T naught onwards, the path is in that neighborhood, no matter how small that neighborhood is. But in particular, there's got to be a point P of the manifold for that. There is no claim, however, that the curve itself actually reaches that point P. And so what we have in this situation here is that, you see, we have a curve here which is, we can write down curves which end here and are not extendable. And see, this is one of those situations where J plus does not contain these events here. So what we need to do is study inextendable curves. Remember, these will be those three cases. The case of interest, gamma hits a singularity. Another case is where gamma, the curve runs off to infinity. Another case is where it's going round and round in a closed time-like curve. Now, before we can get to the singularity theorems and focus on this, we will have to exclude the other cases. But that's interesting in its own right, as you will see. See, today we won't get to the singularity theorems just yet. It's interesting on its own right to consider again this issue of causality in general relativity. We already saw at the very beginning of today's lecture that in order to have a well-defined distinction between past and future, we must have a smooth, non-vanishing time-like vector field. The existence of a smooth, non-vanishing time-like vector field is in one-to-one correspondence to the ability to label the two light cones, the forward and the past light cone, as uniquely future, uniquely past, in a continuous fashion throughout the manifold. Now, that is only guaranteeing that we can distinguish the future from the past. Now we also must address the possibility that there might be closed time-like curves. Because you could have that the future and the past are well distinguished. You can always say in which direction is the future. And yet, there may be closed time-like curves. It may be possible to travel back into the past. It's an additional issue. So we have to consider the possibility that we have paths like this, where these are the forward light cones. And you see, it's always forward light cone, forward light cone, forward light cone, forward light cone. And it's a continuous assignment of what is forward, what is future. It's a continuous assignment in the manifold of what is the future. So we are not contradicting the fact that we've already restricted attention to the case where we have a unique assignment of the future. Even though we have a unique assignment of the future continuously and so on, we can still have closed time-like curves. We can travel to the future, to the future, to the future, and you come back to where you started. Even if you have time orientability. So, what does it take to exclude this? I think this is a tantalizing question. I don't think that the universe has that feature. It's very unlikely that we have closed time-like curves. But what is so tantalizing about it is that general relativity doesn't seem to forbid it. Since the universe doesn't do it, there must be some extra law that does it. There's got to be some extra thing to be discovered, some laws of nature probably, that will make it impossible for this to occur. General relativity does allow it. So there's an opening for us. We can look for new laws of nature that will enforce that. So let's explore what it takes. Here is a causality condition. We say that a space-time is causal if it does not contain closed causal curves. either time or null, either time-like or null. Okay, so space-time is causal if you can't travel to the past. No closed time-like or null curves. This seems to be a plausible condition to pose, but it's by far not satisfactory. And the reason is that a space-time that is causal may be arbitrarily close to being causal. And that would be bad too. See, it could be that the space-time could be arbitrarily close to being acausal in the following way. Remember this picture here, right? So in this merry-go-round here, you just have a closed time-like curve. Now, here is a space-time in the form of a soda can again. Imagine that the light cones are like this. I'm just plotting the future light cones. The past light cones are implied, right? So these are future light cones. Even if they look like ice cream cones, they are future light cones, okay? And so they're all pointing upwards very nicely. And then curvature gets involved, and these light cones are tilted a little bit. And here they are tilted quite a lot. But then they recover, and up here they are not so much tilted, and here they are pretty much ordinary again. And you see, it's almost a crisis here, because these light cones here, they go all around, right? These all around the can. If these light cones were to tilt a little bit too much, then you could have this situation, right? As soon as you have that, this situation arises as soon as the bottom line here of those light cones becomes horizontal. Because then you could travel around this can. Without it, if those are always a little bit up, then you're always traveling this way. You're always traveling upwards, guaranteed. But they could tilt such that they become, that horizontal motion, eternal just horizontal motion suddenly becomes possible. So what we could have is a space-time in which the light cones are such that it is causal according to this definition, but just barely. And the smallest of perturbations, just throw a tennis ball in there, create some extra curvature, some light cones tilt just a little bit more, and suddenly, bang, you have a time-like closed curve. And then it would become non-causal. We like to believe that nature doesn't allow that either, to be so close to acausality. After all, with quantum fluctuations, you can never be so sure where a light cone is and where the matter is and what the curvature does and so on. So we want some stability here. So let's say that a space-time is strongly causal. And you know, I'm really destroying here all hopes of Hollywood to... but anyway, so that's what we want to exclude here, Back to the Future stuff. So we say that a space-time is strongly causal if for all events of the space-time and for all neighborhoods of these events, there is a neighborhood V inside that neighborhood such that no causal curve gamma intersects V more than once. In other words, you have a safety margin. What it means is that for every event of the manifold, you can choose some neighborhood, and within that neighborhood, there is a neighborhood in which you find that the geodesics can only pass through only once. You see, here that would not be obeyed. If this goes very, very close, then you will find some neighborhood in which the geodesics are not completely looping, but they're going around multiple times. And if you can avoid that, then you have a more causal situation. It's more stable against perturbations. Because it would have to go from, you know, just one geodesic going through to suddenly infinitely many going through. Okay, so we say that the space-time is strongly causal if that is the case. And of course, we require strong causality to keep causal curves at least a finite distance from intersecting themselves. It turns out that still arbitrarily small perturbations in the metric somewhere could allow causal curves to self-intersect. So this is like a good attempt, but it's not strong enough. Still not, it looks as if it's more causal, more stable against perturbations, but there is still this stability problem. And that's the key. Arbitrarily small perturbations in the metric could still allow causal curves to self-intersect and therefore to have closed loops. The solution is to enforce it by brute force. Let us perturb the metric. Remember, a spacetime is described by a differentiable manifold with a metric tensor on it. And the metric tensor determines what the light cones are. Let us stick with the same differentiable manifold and its metric tensor, but now consider on top of the usual metric tensor also a perturbed metric tensor, G tilde. And G tilde is the old metric, and then you subtract omega nu, where omega mu is some time-like cotangent vector field. Now we have two spacetimes. We have the spacetime described by G and the spacetime described by G tilde. It turns out that by choosing omega time-like, we don't disturb the signature of G tilde in the sense that it is still -1, 1, 1, 1. Okay, so we perturb the metric. We have really perturbed the shape of the manifold now. G gives the spacetime its curvature. G tilde gives the spacetime another curvature. So we are actually describing perturbations. We're not describing arbitrary perturbations here. We're just describing a particular perturbation of a type that will be useful for the analysis of causality. Let us compare for arbitrary tangent vectors the condition of the tangent vectors to be time-like. So for a tangent vector to be time-like, according to the new metric G tilde, you have that this has to be negative. For the same tangent vector to be time-like with respect to the old metric G, you have that this has to be negative. How are the two expressions related to each other? Let me plot G tilde again. Here it is. So what we find is that VVG tilde is VVG minus V omega V omega. And you see, this might be positive or negative, but the point is it's some number that we are squaring here. So the whole thing is positive, and we are subtracting it. So what we see here is that it is much easier for a vector to be time-like with respect to the metric G tilde than it is for a vector to be time-like with respect to G. Okay? Because a vector might be still space-like with respect to G, so this comes out positive, but we are subtracting stuff. So it might be that V is space-like with respect to G, but it is time-like with respect to G tilde. We've made it easier for a vector to be time-like, which is to say that we have way more time-like curves now, because there are more tangent vectors that are time-like. Imposing causality with respect to G tilde is therefore much more restrictive than imposing causality with respect to G, right? Because there are way more time-like curves with regards to this than that. So the manifold with the metric G tilde has all the causal curves of the spacetime with the metric G, because every vector that was time-like before is still time-like. But it has more causal curves, because more vectors are now time-like. So the definition then is that a spacetime is called stably causal. Stably causal if there exists an omega, a perturbation of G to G tilde. So if there exists an omega, such that if we perturb G with omega, then the manifold with respect to the so obtained metric is causal. Has no closed time-like curves. You see, this is putting now a safety margin there because, yep.
Yeah, if you make the vector omega infinitesimal, wouldn't you have the same problem? Because you're adding something that can be arbitrarily small?
Yes, but we're not allowing it to be infinitesimal. We're allowing it to be small, but it has to be finite. And that just creates a gap. You're right that the gap is small, right? But it's still a gap. And so it doesn't say that it's really very stable. It just says that there is a finite safety margin. It may be very small, but it's finite. And before that condition, before we impose that condition, you can have spacetimes where there's no safety margin. And an arbitrarily small perturbation could screw it up. This is only saying that there is some, you need at least perturbations of a such and such amount that to screw up the causality. Okay, now one can prove that if a manifold is stably causal, then it is also strongly causal. Meaning that, there's always a neighborhood about each point where a geodesic can pass through only once. But the opposite is not true. This is really a stronger condition than the only one geodesic passing through a neighborhood condition is. And this is now getting us, so to speak, it's closing the circle to what we did at the very beginning of today's lecture, and it's the last slide as well. One can prove this nice theorem, namely that a spacetime is stably causal, so there is some safety margin there with regards to perturbations of the spacetime, if there exists a differentiable function f such that the gradient of it is a path-directed time-like vector field. Now, because this is what we can then use for the omega. And this is to be compared with the condition that we had for orientability. For orientability, we needed that for a spacetime to be having a time orientation, we needed that there is a smooth, non-vanishing, time-like vector field. That is guaranteeing, it's if and only if, it's guaranteeing that we can uniquely distinguish the past from the future. And what we just saw with this theorem, and what we had before, is that on top of our time orientability, we get stable causality with a safety margin with maybe small, but a finite safety margin with respect to perturbations of the metric. If there exists a time-like vector field, which is, if there exists a differentiable function f, which generates a path-directed time-like vector field. And that is to say that if we have time orientability, then we have this smooth time-like non-vanishing vector field. If that vector field on top of existing is also the gradient of a function f, if it's not just any vector field but a gradient vector field, then we can conclude that the spacetime is stably causal. Which I think is very nice because that is something you can easily check. Is there such a vector field or not, which is a gradient vector field. And then what is that, the role of that function f? It's a scalar function, right, whose gradient is generating our past and future direction. You can use it as a clock, right, because its gradient is telling you the future, right? So this function f is a scalar function. Think of it as a clock, a cosmic clock, or a field of clocks everywhere, which is such that if you take the gradient of that time function, of the timekeeping function, it's of course always pointing in the time direction, and it's defining stability and future direction and so on. So it's a cosmic time variable, which is really nice, but not unique. Right? There can be many of those. There is, unfortunately, no unique cosmic time variable. Yep.
So when people talk about entropy being like the arrow of time, could we use something like that? Like make entropy of some state or some system to be our scalar function?
Yeah, in principle, that would be nice. If we could say that for some reason there's got to be that function because entropy is increasing, and if this is simply the local entropy density or something like that. But, well, nobody has really pulled it all together. In principle, that's where we would like to go. But well, you would have to, I suppose what you would have to do is invent a clock that's entropy-based. It's not counting oscillations, but instead it's basically counting time as the degree of mixedness of some gases, for example, right? So you could imagine that you take your stopwatch consists of a chamber, a box with two chambers, and one has a blue gas and the other has a yellow gas or whatever. And then at time equals 0, you start your stopwatch by taking out the separating wall between the two chambers. And then by diffusion, the blue and the yellow will mix. Very slowly, but they will mix. The entropy will increase. And you can measure the entropy as a function of time, and you can use that as a clock. There's nothing oscillatory about it, right? And then, so if you could make that watertight, I suppose, yeah. But that's been tried, and nobody's really tied up all the loose ends yet.
It always reaches thermal equilibrium at some point.
It does, but your clock is still running for eternity because you never actually reach the thermal equilibrium. Yeah, I mean, thermal, yes, but in principle, it takes until eternity until it's completely mixed. At least in the thermodynamic limit where you had an infinite amount of gas.
I mean, suppose we take the air of this room, it reaches thermal equilibrium really fast.
Oh no, you would be surprised. When I was an undergrad, in our experimental physics class, the prof had this with water. So he took a water container, and there was a blue dye on top of the water column, and it was just transparent water below. And then at the beginning of the course, at the beginning of the semester, he somehow removed a separating wall between the two. And then you saw still a very sharp line, dividing line, between the blue stuff on top and the clear water below. By the end of the term, it was still almost sharp. The diffusion is extremely slow. If you don't give it any reason to convect, then diffusion alone is really a very slow process. It's basically because random walk is very slow. And the blue molecules are making it in a random walk into the transparent liquid. That's pretty slow. But apart from practical considerations, in principle, yes, you can have an entropy-based clock. And it would be natural to identify the thermodynamic error of time with an error of time that is from GR, but really there's nothing statistical physics about this argument, so it hasn't been properly linked yet. All right, that's it for today. See you on Monday.